1, 2, 3. I am excited to do this chapter because this chapter will introduce a lot of stuff which will lead to a lot of very cool things with abstract algebra. Our stream is working. Let's just get right into it. Chapter 9, Isomorphisms. Many groups may appear to be different at first glance, but can be shown to be the same group by a simple renaming of group elements. For example, Z4 and the subgroup of the circle group T generated by I can be shown to be the same by demonstrating a one-to-one correspondence between the elements of two groups and between the group operations. In such a way, we can say that the groups are isomorphic. Definitions and examples. Two groups, G dot and H circle, are isomorphic if there exists a one-to-one and onto map, phi of G of H, such that the group operation is preserved. That is, phi of A times B equals phi of A composed with B. For all A and B and G. If G is isomorphic to H, we write G, Kong, that's how you write the symbol in LaTeX. Kong is incongruent to H. The map phi is called an isomorphism, so let's write this explicitly out here. So we have G dot and H circle groups. So phi from G to H respects the group operation if phi of A times B is equal to phi of A. Phi of A composed with phi of B. Notice the swapping of the actual operations. And phi is an isomorphism if phi is bijective. So, example 9.1. This is just going to be a ton of examples because there are just isomorphisms are the language of comparing homomorphisms more generally. But when you're talking about simply whether groups are the same or not, isomorphisms are the language in which you talk about that. So, example 9.1. To show that Z sub 4 is isomorphic to the group generated by I, define a map phi from Z sub 4 to the multiplicative group generated by I by phi of n is equal to I to the n. We must show that phi is bijective and preserves the group operation. The map phi is one-to-one and onto because phi of 0 equals 1, phi of 1 equals I, phi of 2 equals negative 1, and phi of 3 equals negative I. As well with this, because no two elements map to the same output element, and every element in the cyclic group generated by I is here, that's how we know it's bijective. Since phi of m plus n is equal to I of m plus n equals I of m I n n equals phi of m times phi of n, the group operation is preserved. Notice that we've changed this addition here to a multiplication. Example 9.2. We can define an isomorphism phi from the additive group of real numbers r plus to the multiplicative group of positive real numbers r plus I might call that r plus and c dot, because that's again what you call that symbol in LaTeX, with the exponential map. That is, phi of x plus y is equal to e to the x plus y equals e to the x, e to the y equals phi of x, phi of y. Of course, we must still show that phi is one-to-one and onto, but this can be determined using calculus. Example 9.3. The integers are isomorphic to the subgroup of q star consisting of elements of the form 2 to the n. Define a map phi from z to q star by phi of n equals 2 to the n. Then phi of m plus n equals 2 to the n plus n equals 2 to the m 2 to the n equals phi of m times phi of n. By definition, the map phi is onto the subset 2 to the n and z of q star. To show that the map is injective, assume that m is not equal to n. If we can show that phi of m is not equal to phi of n, then we are done. Suppose that m is greater than n, and assume that phi of m equals phi of n. Then 2 to the m equals 2 to the n, or 2 to the m minus n equals 1, which is impossible since m minus n is greater than 0. So this is commonly something when you something that you try to show for showing isomorphisms, and that's that phi of m, phi of n, basically, if you have phi not being bijective, like a operation that respects the, actually, you know what, no, these notes are actually very valuable, I'll just move these off to the side. So if phi respects the group operation, but is not injective, that means phi of m equals phi of n. But remember, we're working in a group, so we have that phi of m, phi of n to the negative 1, phi of n to the negative 1 is equal to the identity element e, or we'll call it 0 in this case. However, because this is a homomorphism, this is actually equal to phi of m, phi of negative n is equal to 0, and then because this respects the group operation, phi of m minus n is equal to 0. Now notice that since m is not equal to n, this means that m minus n is not equal to 0. So saying that a map is injective is the same as saying that if m minus n is not equal to 0, then m minus n can never be equal to 0. Phi of m minus n can't be equal to 0 in the new group, because that would imply that in the old group we have a non-zero element that maps to 0, which means two elements are equal. So roughly, a lot of these examples showing that things are isomorphisms will be things where it will show the injectivity by showing that if a non-zero element maps to 0, that's impossible. That will produce a contradiction. So, example 9.4. The group z sub 8 and z sub 12 cannot be isomorphic since they have different orders. However, it is true that u of 8 is congruent to u of 12, or is isomorphic to u of 12. We know that u of 8 is equal to 1, 3, 5, 7, and u of 12 is equal to 1, 5, 7, 11. An isomorphism u of 8 to u of 12 is then given by 1 goes to 1, 3 goes to 5, 5 goes to 7, and 7 goes to 11. The map phi is not the only possible isomorphism between these two groups. We can define another isomorphism by phi of psi of 1 equals 1, psi of 3 equals 11, psi of 5 equals 5, and psi of 7 equals 7. In fact, both of these groups are isomorphic to z cross 2 times z cross 2. Example 9.5. Even though S3 and Z6 possess the same number of elements, we would suspect that they are not isomorphic, because Z sub 6 is abelian and S sub 3 is not abelian. To demonstrate this is indeed the case, suppose that we have some isomorphism Z sub 6 to S sub 3. Let A, B, and S3 be two elements A, B is not equal to BA. Since phi is an isomorphism, and thus onto, there exist m and n in Z sub 6, such that phi of m is equal to A, and phi of n equals B. However, AB is equal to phi of n is equal to phi of m plus n, is equal to phi of n plus m. Notice that in this step we use the commutivity of Z sub 6 to reverse these, equals phi of n, phi of m, equals BA, which contradicts the facts that A and B do not commute. Theorem 9.6. Let phi from G to H be an isomorphism of two groups. Then the following statements are true. 1. Phi to the negative 1 from H to G is an isomorphism. 2. The order of G is equal to the order of H. 3. If G is abelian, then H is abelian. 4. If G is cyclic, then H is cyclic. 5. This one is especially important for things we'll be doing later. If G is a subgroup of, or if G has a subgroup of order n, then H has a subgroup of order n. Proof. Assertions 1 and 2 follow from the fact that phi is a bijection. We will prove 3 here, and leave the remainder of the theorem to be proved in the exercises. 3. Suppose that H1 and H2 are elements of H. Since phi is onto, there exist G1 and G2 in G, such that phi of G1 equals H1 and phi of G2 equals H2. Therefore, H1, H2 equals phi of G1, phi of G2 equals phi of G1, G2 equals, using the commutativity at this step, equals phi of G2, G1 equals phi of G2, phi of G1 equals H2, H1. We are now in a position to characterize all cyclic groups. Theorem 9.7. All cyclic groups of infinite order are isomorphic to the integers. Proof. Let G be a cyclic group with infinite order, and suppose that A is a generator of G. Define a map phi from Z to G by phi of n goes to A to the n. Then, phi of m plus n equals phi of m plus n equals A to the m, A to the n equals phi of m, phi of n. To show that phi is injective, suppose that m and n are two elements in Z, where m is not equal to n. We can assume that m is greater than n, otherwise we just swap around n and m. We must show that a to the m is not equal to a to the n. Let us suppose the contrary, that is, am equals a to the n. In this case, a to the m minus n equals e, where m minus n is greater than 0, which contradicts the fact that a has infinite order. Our map is onto, since any element in G can be written as a to the n for some integer n, and phi of n equals a to the n. Now, something really powerful here is that since all cyclic groups are of infinite order and are isomorphic to the integers, we have no infinite cyclic group. We have no infinite cyclic group such that the cardinality of that group is greater than the integers. So greater than or equal to the real numbers if you assume the continuum hypothesis false, which gives us a very strong upper bound on the set theoretic cardinality of certain infinite groups. That won't be discussed in this book, that's not important to this book, but it's a really interesting fact to come out of this theorem. Theorem 9.8. If G is a cyclic group of order n, then G is isomorphic to Z sub n. Proof. Let G be a cyclic group of order n, generated by A, and define a map phi from Z sub n to G by phi sends k to a to the k, where 0 is less than or equal to k is less than n. The proof that phi is an isomorphism is one of the end of chapter exercises. Corollary 9.9. If G is a group of order p, where p is a prime number, then G is isomorphic to Z sub p. Proof. The proof is a direct result of corollary 6.12. Another way you can think about it is that every group contains a cyclic group, and if a subgroup has a order of a prime, then every element in that group generates the same group of order p. Because it's prime, so the order of the group generated by that element in that subgroup must divide the order of the subgroup. And since the order of that subgroup is prime, and there's more than one element in there, because there's E and that element, then by definition we have that subgroup, cyclic group generated by that. Cyclic group generated by that is the entire subgroup we're talking about. And then just changing subgroup to group in that discussion, we get that result. The main goal in group theory is to classify all groups. However, it makes sense to consider two groups to be the same if they are isomorphic. We state this result in the following theorem, whose proof is left as an exercise. Theorem 9.10. The isomorphisms of groups determine an equivalence relation on the class of all groups. Hence, we can modify our goal of classifying all groups to classifying all groups up to isomorphism. That is, we will consider two groups to be the same if they are isomorphic. Cayley's theorem. Cayley proved that if G is a group, it is isomorphic to a group of permutations on some set. Hence, every group is a permutation group. Cayley's theorem is what we call a representation theorem. The aim of representation theory is to find an isomorphism of some group G that we wish to study into a group that we know a great deal about, such as a group of permutations or matrices. So, for example, 9.11, consider the group Z sub 3. The Cayley table for Z sub 3 is as follows. So it's just normal mod 3 addition. The addition table of Z3 suggests that it is the same as the permutation group G equals 0, 1, 2, 0, 0, 1, 2, 0, 2, 1. The isomorphism here is 0 goes to 0, 1, 2, 0, 1, 2, 1 goes to 0, 1, 2, goes to 1, 2, 0, and 2 goes to 0, 1, 2, goes to 2, 0, 1. Another way of saying it is notice that 0 has a permutation under it. So 0 goes to 0, 1 goes to 1, 2 goes to 2. Then, 1 has the permutation 0 goes to 1, 1 goes to 2, 2 goes to 0. And then 2 has the permutation 0 goes to 2, 1 goes to 0, 2 goes to 1, which is exactly the permutations described here. This is part of why, if you had watched the video on permutation groups, I had stressed that result so strongly, because that is in fact a preview of Cayley's theorem. So, theorem 9.12. Cayley, every group is isomorphic to a group of permutations. Proof. Let G be a group. We must find a group of permutations G bar that is isomorphic to G. For any G in G, define a function lambda sub G, G to G, by lambda G of A is equal to G of A. So we'll call this left multiplication by G. We claim that phi of G is a permutation of G. To show that lambda of G is 1 to 1, suppose that lambda G of A is equal to lambda G of B. Then GA equals lambda G of A equals lambda G of B equals GB. So by left cancellation, we have that A is equal to B. To show that lambda G is onto, we must prove that for each A and G, there is a B such that phi of G of B is equal to A. For this, simply let B equals G to the negative 1, A. Now we are ready to define our group G bar. Let G bar equal the set of all lambda G for G and G. We must show first that G bar is a group under a composition of functions and find an isomorphism between G and G bar. We have closure under composition of functions since lambda G composed of lambda H of A is equal to lambda G of H of A is equal to GH of A is equal to lambda GH of A. Also, lambda E of A is equal to EA is equal to A, and lambda G to the negative 1, lambda G of A equals lambda G to the negative 1 G of A equals G to the negative 1 G of A equals lambda E of A. We can define an isomorphism from G to G bar by phi of G is sent to lambda of G. The group operation is preserved since phi of GH equals lambda GH equals lambda G lambda H equals phi of G phi of H. It is also 1 to 1 because if phi of GA is equal to phi of HA, then GA equals lambda GA equals lambda HA equals HA. Hence, GH is G is equal to H. That phi is onto follows from the fact that phi of G equals lambda G for any lambda G in G bar. The isomorphism G goes to lambda G is known as the left regular presentation of G, or representation of G. And this is where I bring in a bit of category theory, but only a very small amount. So what's very special about this theorem is that we can think of a group as two ways. First, a group is like, we have all these elements here, right? Like all these elements in the set G, where like this and this combined together, we can link these together to make that. We have maybe as well like that and that line linked together to make that, right? We have this like pairwise view of the set G. However, we could also think of it another way. We can think of the group G as a single element G, and what we actually care about are the functions from G to itself. Notice here that, for example, one function might be lambda G prime, along with, while we just make sure we have one lambda E. So this, we think of instead of the objects in a set, we think of the set as itself an object. And talking about the group is more so talking about the morphisms that you can apply to the group, the representation of the group if the set is considered an object in and of itself. And this forms a basis for very nice descriptions of groups, category theoretically, and allows us to then talk about groupoids. But that's all I'm going to say on that. I will say though, that this representation theorem may seem trivial, like of course we can define like a permutation, by just like multiplying objects, but it's way less trivial than it seems initially. Anyways, okay, continuing. Historical note. Arthur Cayley was born in England in 1821, though he spent much of the first part of his life in Russia, where his father was a merchant. Cayley was educated at Cambridge, where he took the first Smith's Prize in mathematics. A lawyer for much of his adult life, he wrote several papers in his early 20s before entering the legal profession at the age of 25. While practicing law, he continued his mathematical research, writing more than 300 papers during this period of his life. This included some of his best work. In 1863, he left law to become a professor at Cambridge. Cayley wrote more than 900 papers in fields such as group theory, geometry, and linear algebra. His legal knowledge was very valuable to Cambridge. He participated in the writing of many of the university statutes. Cayley was also one of the people responsible for the admission of women to Cambridge. So Cayley's a pretty cool dude. 9.2. Direct products. Given two groups G and H, it is possible to construct a new group from the Cartesian product G and H, G of G and H, G times H. Conversely, given a large group, it is sometimes possible to decompose that group. That is, a group is sometimes isomorphic to the direct product of two smaller groups. Rather than studying a large group G, it is often easier to study the components of G. So external direct products. This is actually, I think I covered this in like my second or third stream, but I can just like offhandedly mention it. If G dot and H composition are groups, or if G dot and H circle are groups, then we can make the Cartesian product of G and H into a new group. As a set, our group is just the ordered pairs G, H in G times H, where G is in G and H is in H. We can define a binary operation on G times H by G1 H1 times G2 H2 equals G1 dot G2 H1 circle H2. That is, we just multiply elements in the first coordinate as we do in G and elements in the second coordinate as we do in H. We have specified the particular operations dot and circle in each group here for the sake of clarity. We usually just write G1 H1 times G2 H2 equals G1 G2 H1 H2. Proposition 9.13. Let G and H be groups. The set G times H is a group under the operations G1 H1 G2 H2 equals G1 H1 G1 G2 H1 H2, where G1 G2 in G and H1 H2 is in H. First, clearly the binary operation defined above is closed, as in any multiplication of two elements is well defined. If EG and EH are the identities of the groups G and H respectively, then EH is the identity of G times H. The inverse of GH and G times H is G to the negative 1, H to the negative 1. The fact that the operation is associative follows directly from the associativity of G and H. Example 9.14. Let R be the group of real numbers under addition. The Cartesian product of R with itself, R times R equals R squared, is also a group, in which the group operation is just addition in each coordinate. That is, AB plus CD equals A plus C, B plus D. The identity is 0, 0, and the inverse of AB is negative A, negative B. Just as a kind of preview, this is where, for a lot of linear algebra uses, this is kind of a preview that we can use group theory as a more basic language to talk about the constructions of linear algebra. And we can generalize from there, especially when we get to ring theory. Anyways, continuing. Example 9.15. Consider Z mod 2 times Z mod 2, which is the four-element set 0, 0, 0, 1, 1, 0, and 1, 1. Although Z2 and Z2 times Z2 and Z4 both contain four elements, they are not isomorphic. Every element A, B in Z2 times Z2, other than the identity, has order 2, since A plus B plus A plus B equals 0, 0. However, Z4 is cyclic. The group G times H is called the external direct product of G and H. Notice that there is nothing special about the fact that we have only used two groups to build a new group. The direct product from the pi, I might call that product from I equals 1 to n equals G of I, or the pi of I equals 1 to n of G sub I, which is equal to G1 times G2 all the way to times Gn, of the groups G1, G2, all the way up to Gn, is defined in exactly the same manner. If G equals G1, G2, all the way up to Gn, we often write Gn instead of G1, G2, all the way to Gmn. Also, this does work for infinite products, but it's just very messy to write out, and we're going to get to some stuff soon where the fact that it's finite is actually an important part of what we're doing. So, example 9.16. The group z sub 2 to the n, considered as a set, is just the set of all binary n tuples. The group operation is the exclusive OR of two binary n tuples. For example, 0, 1, 0, 1, 1, 1, 0, 1, plus 0, 1, 0, 0, 1, 0, 1, 1, equals 0, 0, 0, 1, 0, 1, 1, 0. This group is important in coding theory, in cryptography, and in many areas of computer science, as you have seen if you've seen the last stream. Theorem 9.17. Let G, H be in G times H. If G and H have finite orders R and S respectively, then the order of G, H, and G times H is the least common multiple of R and S. Proof. Give me a second. I've gotten myself a cold, that's why I was sneezing earlier, apologies for that. Theorem 9.17. Let G, oh yeah, I've already read that. Okay, proof. Suppose that M is the least common multiple of R and S, and let N be equal to the order of G and H. Then, GH to the M is equal to G to the M, H to the M, equals EGEH, and G to the N, H to the N, equals GH to the N, equals E to the G, E to the H. Hence, N must define M, and N is less than or equal to M. However, by the second equation, both R and S must divide N. Therefore, N is a common multiple of R and S. Since M is the least common multiple of R and S, M is less than or equal to N. Consequently, M must be equal to N. Corollary 9.18. Let G1 all the way up to Gn be in the product of Gi. If G sub I has finite order Ri and Gi, then the order of G1 all the way up to Gn and pi of Gi is the least common multiple of R1, R2 up to Rn, which is just applying that in each individual case. Example 9.19. Let 8, 56 be in Z mod 12 times Z mod 60. Since GCD of 8 and 12 is equal to 4, the order of 8 in 12 over 4 equals 3, in 3 in Z mod 12. Similarly, the order of 56 in Z mod 60 is 15. The least common multiple of 3 and 15 is 15. Hence, 8, 56 has order 15 in Z mod 12 times Z mod 60. Example 9.20. The group Z mod 2 times Z mod 3 consists of the pairs 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. In this case, unlike that of Z mod Z2 times Z2 and Z4, it is true that Z mod 2 times Z mod 3 is congruent to Z mod 6. We need only show that Z mod 2 times Z mod 3 is cyclic. It is easy to see that 1, 1 is a generator for Z mod 2 times Z mod 3. The next theorem tells us exactly when the direct product of two groups is cyclic. Theorem 9.21. The groups Z mod M times Z mod N is isomorphic to Z mod Mn if and only if the greatest common divisor of M and N is equal to 1. Proof. We will first show that of Z mod M times Z mod N is isomorphic to Z mod Mn, then the greatest common divisor of M and N equals 1. We will prove the contrapositive. That is, we will show that if the GCD of M and N is equal to D is greater than 1, then Z mod M times Z mod N cannot be cyclic. Notice that Mn over D is divisible by both M and N. Hence, for any element A, B in Z mod M times Z of N, A plus B plus A plus B plus on and on, Mn over D times is equal to 0, 0. Therefore, no AB can generate all of Z mod M times Z mod N. The converse directly follows from theorem 9.17, since LCM of Mn equals Mn if and only if the GCD of Mn equals 1. Corollary 9.22. Let n1 all the way to nk be positive integers. Then, the product of I equals 1 to k equals z sub n sub I is isomorphic to the product z sub n1, n2 all the way to nk, if and only if the greatest common divisor of ni and j equals 1, for I not equal to j. Corollary 9.23. If m is equal to p1e1 all the way to pk-ek, where the pi's are distinct primes, then zm is congruent to z sub p1 to the e1 times z sub p2 to the e2, all the way to times z sub pk to the ek. Proof. Since the greatest common divisor of p sub I, e sub I, and p sub j, e sub j for 1 is I not equal to j, The proof follows from Corollary 9.22. In Chapter 13, we will prove that all finite abelian groups are isomorphic to direct products of the form z sub p1 e to the 1 times all the way on 2 times z sub p to k to the ek, where p1, pk are not necessarily distinct primes. That is going to be under a label of something called the fundamental theorem of finitely generated abelian groups, but we will get there when we get there. So internal direct products. The external direct product of two groups builds a large group out of two smaller groups. We would like to be able to reverse this process and conveniently break down a group into its direct product components. That is, we would like to be able to say when a group is isomorphic to the direct product of two of its subgroups. Let G be a subgroup with B be a group with subgroups H and K, satisfying the following conditions. 1. G is equal to HK, which is the set of all H times K for H and K's and K. 2. The intersection of H and K is the trivial group. 3. HK is equal to KH for all K and K and H and H. Then G is the internal direct product of H and K. Example 9.24. The group U8 is the internal direct product of H equals 1, 3 and K equals 1, 5. Example 9.25. The dihedral group D6 is an internal direct product of its two subgroups, H equals ID R cubed and K equals ID R squared R4 S R squared S R4 S. It can easily be shown that K is isomorphic to S3. Consequently, D sub 6 is congruent to Z mod 2 times S sub 3. Example 9.26. Not every group can be written as the internal direct product of two of its proper subgroups. If the group S3 were an internal direct product of its proper subgroups, H and K, then one of the subgroups, say H, would have to have order 3. In this case, H is the subgroup 1, 1, 2, 3, 1, 3, 2. The subgroup K must have order 2, but no matter which subgroup we choose for K, the condition that HK equals KH will never be satisfied for H and K and K. Theorem 9.27. Let G be the internal direct product of subgroups H and K. Then G is isomorphic to H times K. Proof. Since G is an internal direct product, we can write any element G in G as G equals HK for some H and K. Define a map phi from G to H times K by phi of G equals HK. The first problem that we face is to show that phi is a well-defined map. That is, we must show that H and K are uniquely determined by G. Suppose that G is equal to HK is equal to H prime K prime. Then H to the negative 1 H prime is equal to K to the K times K prime to the negative 1 is in both H and K, so it must be the identity. Therefore, H equals H prime and K equals K prime, which proves that phi is indeed well-defined. To show that phi preserves the group operation, let G equal H1 K1 and G2 equals H2 K2, and observe that phi of G1 G2 equals phi of H1 K1 H2 K2 equals phi of H1 H2 K1 K1 equals H1 H2 K1 K2 equals H1 K1 times H2 K2 equals phi of G1 times phi of G2. We will leave the proof that phi is 1-to-1 and onto as an exercise. Example 9.28. The group Z sub 6 is an internal direct product isomorphic to 0 2 4 times 0 3. We extend the notion of an internal direct product G to a collection of subgroups H1, H2 all the way to Hn of G by requiring that 1. G is equal to H1, H2 all the way to Hn. 2. H sub I, intersection with the union of all J not equal to I, Hj, is equal to the trivial subgroup. And 3. Hi, Hj equals Hj, Hi for all Hi in Hi and all Hj in Hj. From here, we will leave the proof of the following theorem as exercise. Theorem 9.29. Let G be the internal direct product of subgroups H sub I, where I equals 1, 2, all the way to n. Then G is isomorphic to the product sub I of H sub I. Okay. So, we're not worrying about stage. So, determine the order of 1, 2 in Z sub 4 times z sub, is that an 8? That looks like an 8 to me, but that's like really low quality, and it's like sometimes when I zoom in, it removes my ability to scroll, so I'm not going to worry about that. So each of these, 4 is the minimum for 1, and 4 is the minimum for 2 as well. So this element has order 4. If it's 4 and 6, then the order is order 3. Yeah, because the least common multiple of 4... Oh wait, no, it would be 12 in that case, yeah. Or it would be either 12 or 3. List 3 properties of a group that are preserved by an isomorphism. The group operation, injectivity, and surjectivity. So like the group operation, the cardinality, and identity. 3. Find a group isomorphic to Z15 that is an external direct product of 2 non-trivial groups. So this should be Z sub 3 times Z sub 5 for that. Explain why we can now say the infinite cyclic group. So we can say the infinite cyclic group because any cyclic group that is infinite will be isomorphic to the integers uniquely. Compare and contrast external direct products and internal direct products. External direct products tell you how to construct out of 2 groups with no supposed like relation beforehand a new group, while the internal direct products already has information beforehand and you're working backwards to find valid subgroups such that the internal direct products exist. Alright, and we have a fair number of exercises here, so I'm just going to make my intermission quick and then we will get started. We will probably have a long night of exercises tonight, so Alright, I'm back and I am ready to give this a go. Let me just quick make sure that my stream is, working before I begin this. Alright, let me also put the side of the workboard while I'm waiting for this. Alright, oh gosh. My bitrate has apparently gotten unstable. So we'll see how this goes. Hopefully it works. Alright, loading up the stream again to just double check that everything is working. Alright, we're loading in. It says that my bitrate exists, which is nice. I assume from how it usually goes at this point that I'm in. Let's see. Oh wait, am I still at the intermission screen on this? Or is it just taking a moment to load in? Okay. I'm technically in. That's what we need. That's what we need. Alright, so. Oh, that's also because I probably didn't switch scenes yet. I was just being dumb. Okay. U8 is, okay, we're not working that. Okay. Prove that the integers are congruent to the integers mod n, or n greater than 0. So suppose n is not equal to 0, and define phi from z to nz by phi of n, or no, I shouldn't say n, that's a horrible example to use. Phi of m equals nm. So obviously, for this, it should be clear that this is a one-to-one and onto map, just because we're working with integers. As well, phi of 0 equals n times 0, which is just 0. So phi of 0 equals n0 equals 0. And to show the group operation is preserved, which is the main thing we're worried about, is phi of m plus m prime equals n. Oh gosh, okay. N m plus m prime equals n m plus n m prime equals phi of m plus phi of m prime. So we have a natural isomorphism from the integers to the integers multiplied by n. Okay. Prove that C star is isomorphic to the subgroup GL2R consisting of matrices of the form AB, negative B, A. So define phi, in this case, to be from phi star to this group, we'll call it X. And I'll note that it's a subset of GL2R. And we'll define it by phi of A plus BI is equal to A, if I remember it's negative BB, right? Yeah. So first, we need to show that this map is well defined. So determinant of A, negative B, B, A is equal to A squared minus B squared. AD minus B. So if A squared is minus B squared is equal to 0 in this case, that would imply that A squared is equal to B squared. Wait, let me double check. This seems like it could be wrong. Matrices of AP negative BA. Oh wait, no, it's a squared. I'm being dumb. Yes, it's a squared plus b squared. And obviously this is only 0 if a and b are equal to 0, because a and b are both real numbers. So this is a well-defined map. To show that this map is also as well, every element in this can be written, like, literally just going between these conversions are reading off the rows and columns of the matrices. And we've also shown that if the determinant of this is not equal to 0, then the determinant then a plus or ai either a or b are not equal to 0, so a plus bi is not equal to 0. So continuing on, we need to show that this preserves the group operation. So phi of a plus bi times c plus di is equal to phi of ac minus bd plus ADI plus BCI, or we could just write it under plus AD plus BC I. So this is equal to the matrix AC minus BD, AC minus BD, BD, we have AD plus BC, and negative AD minus BC. Now, what we want to prove is that if this is a homomorphism, it should be equal to the product A, negative B, C, negative D, which this is equal to AC minus BD. Yeah, that's correct. Then we have negative AD minus BC. Then we have BC plus AD. And then we have AC minus BD. So we can then show that there's equality between these two, which shows that this is equal to phi of A plus BI, phi of C plus DI, C plus DI, which completes the proof. Also, I know I've been recently, I don't know if it's just me, but there's been a surge of mathematics channels covering things like splitting extensions, extended and triplex numbers, and a lot of these have things to do with matrix representations, so that's not exactly an invaluable exercise to do. So prove or disprove, U8 is congruent to, is isomorphic to C sub 4. So U8, or I should write it as this, U of 8 is equal to the set 1, 3, 5, 7. Since, as a reminder, U of 8 is U of 2 to the 3. So we know 3 is idempotent. 3 times 3 equals 9, gets sent to 1. 5 times 5 is equal to 24, 25 is also sent to 1. And already we have a contradiction. We can show that U8 is not isomorphic to Z sub 4. Because in Z sub 4, the only, like, we're going to have 1 sent to 1, 1 squared sent to 1, 3 squared sent to 1, and 5 squared sent to 1. And also, if I remember correctly, we're also going to have 7 sent to 1. And we have, for example, 1 plus 1 is equal to 2, not equal to 0. So in Z sub 4, we don't have every element being what we call idempotent, that is sent to our identity. But in this, we have that every element is idempotent. So we have that Z sub 4 is not isomorphic to U sub U8. Alright, clear that. Prove that U8 is isomorphic to the group of matrices. The big thing to note here is that, like, you can just call this 1, this 3, this 5, this 7, and they interact in exactly the way that you expect. For example, every one of these elements is idempotent. 3 times 5 goes to 7. 5 times 7 goes to 3, and then, like, all the respective things. For this, I'll leave this as an exercise to the viewer to do. It's like pure computation. Show that U5 is isomorphic to U10, but U12 is not. Wait, I'm trying to think. What does it mean by that? U12 is not isomorphic to U10? Okay. So let's write this out. U of 5 equals 1, 2, 3, 4. U of 10 is equal to U of 2 times 5 is equal to 1, 3, 7, 9. U12 is equal to U of 2 times 2 times 3 is equal to 1, 5, 7, 11. Yes. Now. Okay. We have an idempotent in none of these. Alright, so 2 squared is equal to 4, 3 squared is equal to 9, and 4 squared is equal to 16. So 4 is the only element in this sent to 1. In U10, we have 9 squared is equal to 81. It's U sent to 1, but every other element is not sent to 1. In U12, 5 times 5 equals 25, sent to 1. 7 times 7 is equal to 42. 11 times 11 is equal to 121, which is sent to, okay. So, in U12, we have 2 elements that are sent to 1. But in U5 and U10, we only have 1 element sent to 1. So we can't have 2 groups isomorphic if they both send different numbers of elements to your identity element under, like, squaring. So, also we can construct an explicit isomorphism between U5 and U10, but it's more interesting to show that U10 and U12 are not isomorphic in that case. Show that the nth roots of unity are isomorphic to Z sub n. This is just an application of the de Moivre's theorem. Show that any cyclic group of order n is isomorphic to Z sub n. Oh yeah, it said to leave this as an exercise. So suppose that we have a group G such that there's an element A in G with the order of A is equal to n, and the cyclic group is equal to G. Now define phi from Z sub n to G, which sends n to a to the n. Clearly, this is a one-to-one and onto mapping. So the main difficulty will be showing the group composition, or the operation is preserved. So phi of m plus n. So like, suppose in this case that m plus n is congruent to k, or actually that's p, yeah, let's use p and q. P plus q is congruent to k mod n. So we have that p plus q minus k is equal to cn, or cn. So we have that p plus q is equal to cn plus k. So phi of m plus n is equal to a to the n plus n is equal to a to the, or no, I should relabel and use a correct notation that I previously established. So phi of p plus q is equal to a to the p plus q equals a to the cn plus k is equal to, I'm going to just do a quick swoop up here, is equal to a to the cn, a to the k is equal to a to the k. So it respects the group operation in this case. And it again is a characterization, kind of like the infinite case. It's a characterization of the of all cyclic groups. So, or all finite cyclic groups. So prove that Q is not isomorphic to Z. This is because we've shown previously that Q is not cyclic, while Z is cyclic. We have that proof that G stars is isomorphic to the multiplicative. Okay, we've shown already that this is a group under the operation, but we have not shown the isomorphism. So, okay, so we have, so this would be something that, since we have, if I remember correctly, 0 as identity in this. Alright, is 0 identity? Yeah, 0 would be identity. So 0 is mapped to 0 in this. So like, suppose we have R to, what are we calling this? We have R star and we have G. So let's think about what would imply a group of R star to be. So that would imply that if we had such a function, phi of A, B equals phi of A star phi of B is equal to phi of A plus phi of B plus phi of A phi of B. So in this example, if B is equal to 1, then we have that phi of A is equal to phi of A plus phi of 1 plus phi of A phi of 1. Oh wait, this is weird. Because we have a reference. So we have phi of this fundamentally then says that if phi of A B is equal to phi of A star phi of B, and phi of okay, let's think of going in the reverse direction, right? What if we think of a function which smooth, okay. So phi of A star B is equal to phi of A phi of B. And note that A star B is equal to phi of A plus B plus AB. Oh god, I've done this before. I'm just like forgetting how this goes. Find a binary operation, prove that she's a group under this. So it's gonna be non-zero real numbers. A plus B plus AB. I mean, wait, we can't factor that. Not really. Oh wait, no, we can. No, we can. This is equal to phi of A. Phi of A times one plus B plus P. Now I can. So 0 is again the identity element? Yeah, B is like 0 is the identity element. So in this way we have 0 is sent to 1. So if 0 is sent to 1, we should have -1 gets sent to 0, which is making me think of a shifting operation. It's like we define it by x minus 1, or no, yeah, x plus 1. So like let's just try it and see how it goes. So our first guess is going to be that we have a function phi. Oh, God, I'm writing this all backwards. Such that phi of x equals x plus 1. I definitely have a feeling that this is going to be the whole picture, but let's see. So phi of x star y is equal to phi of x plus y plus xy is equal to x plus y plus xy plus 1 equals x plus 1 times y plus 1. Oh my god, that was actually it. Now I'm wondering, Is this how we define all, like... Is this how we define all groups isomorphic to the real numbers on the real numbers by these types of, like, rigid transformations? Oh, okay, this is funky. Which is equal to phi of x, phi of y. And obviously this function is 1-to-1 and onto for x not equal to 0, because when x is or x not equal to -1, because -1 is when this equals 0, which isn't in this, so it wouldn't be defined even. But because we're excluding -1, this works, and because it's linear, we're just going to a priori assume that it's onto. Oh, sick. Okay, that was actually really satisfying. That was a complete guess, but that was a very lucky guess. Alright. Show that the matrices form a group. No. Oh gosh, should I? I'm thinking it's gonna be S3. Because, yeah, this is permuting the second and third elements. This is permuting the first and second. This is permuting, this is sending 2 to 1, then 1 to 3, then 3 to 2. This is sending 3 to 1. Yeah, this is all permutations, just in matrix representation of, like, the 3 column matrices. Alright. Find 5 non-isomorphic groups of order 8. Sorry, but no. 12. Prove S4 is not isomorphic to D12. Probably, I'm thinking something along the lines of... I'm thinking something of, like, D12 does not have a element of... Actually, 4 factorial is equal to 6 times 4 is equal to 24. Actually, no, never mind. You have to use some more specific arguments for that. And I'm lazy. Okay, let W equal omega equals 6. No. I don't want to be working with more matrices. Please stop. Okay. It's cool that we have these matrix representations. But I'm more so curious about when we ever have a matrix representation. And at what times we have that. That, though, I do not know. List all the elements of... Oh, this is just a cop-out. List all the elements of that? Oh, man. Find the orders of each element. Prove that D4 cannot be the internal direct product of its proper subgroups. Alright, these look like better things, including this one. This looks like a really good exercise. Prove that the subgroup of Q star consisting of the elements 2 to the m, 3 to the n for mn is an internal direct product isomorphic to z times z. I mean, this is a product of two things. For the rationals, I mean, we don't have something like 1/7 in this form, so it isn't the entirety of Q star. I'm just slightly confused. Well, how much it's asking, but okay. Is an internal direct product isomorphic to z times z? So fundamentally, it's basically asking that it's 1-to-1 and onto. And it will come down to the form that we have different prime factorizations here. Oh god, I remember this being particularly ugly. Prove it is for every abelian group of order divisible by 3 contains a subgroup of order 3. Every abelian group of order divisible by 3 contains a subgroup of order 3. I feel like this is going to be something that comes down to, like, fundamental theorem of finite abelian groups. Of order divisible by 3. I actually have no idea. So like suppose that the order of G 3 divides the order of G. So we can call G is equal to E, we have G1, 1, G2, 1, G3, 1, on and on. So that order of G is equal to 3n. I also wonder about the fact that this is a abelian. Definitely, actually, it's going to matter that it's a abelian. So let's take an element not equal to the identity. G is not equal to the identity. We'll have order equals n. Let's say that n is not equal to 3. Then G minus the group G, the cardinality of that is equal to 3n minus order of G. I'll put the brackets around there because this actually refers to a quotient group. So like if we cut out that cyclic group, we have that. So then if we cut out that cyclic group, if it's equal to, if the group is cyclic and its order is divisible by 3, then like very obviously we're going to have 3, like it's going to be, since it's divisible by a prime, there's going to be some element, because it's cyclic, isomorphic to Z mod n, going to just like be that. But we need to show in this case Zn minus 3. Since since the order of G divides n, and it doesn't, it may divide 3. So the order of G equals PQ, where P divides 3n. So we have is equal to 3n minus PQ. Actually, I don't know how I want to phrase this. So 3n minus order of G. Then we're going to have, we have a process. We have E is not equal to G1. Then we take some G2 in G minus the order of G. And then we have that G. We'll basically do this operation where we keep cutting up these cyclic groups. And at all times, these cyclic groups have to not have order equal to 3. But that ultimately means that, okay, I think I know how I want to phrase this. Basically, suppose that G is equal to, the order of G is equal to some prime times Q, or times n. we will have an algorithm. First, it selects some G1 not equal to the identity, not equal to E, or yeah, G1 in G for G1 not equal to G, or not equal to E. And we will form the cyclic group G. In this case, okay, yeah. And we'll form the group G1 equals the cyclic group G1. Now, if G1 is divisible by the prime, then if G1 is divisible by the prime, then by not by fundamental theorem of finite abelian groups, then since P is a prime, we'll have G1 be congruent to Z mod P times something, which implies that there's going to be some element in this with order P, which implies that there'll be some element in the cyclic group generated by G1 of order P. Now, note at this point that G1 minus G1 set minus has cardinality less than G. At this point, we will call G G naught. Call G naught. G equals G naught. Now, we choose some G2 in G1 minus G naught. G1 minus G1. And if its order divides P, then again, it's going to, so if its order divides P, it's going to again be it, so we assume that it's not the case. So we have the order of G2. Actually, I should quick specify this. G naught. G naught minus G1. Order less than G naught. We have G2 is in G naught minus G1. The order of G. So G1 is equal to G2 is equal to G naught minus G2, which is less than G1. So now we have an algorithm that chops our things into cyclic groups of prime order. And we know that eventually that's kind of eventually we'll have there'll be some GI because our group is finite. These inequalities confirm that we're going to eventually have some GI, such that GI minus 1 minus GI is equal to the empty set. Now, suppose that we suppose that G1, G2, P does not divide G1, G2 all the way up to Gi minus 1. So P divides G1, G2 all the way to Gi. Oh god. So then, if P does not divide all those. It's Gi minus 1. Now, I'm wondering what information we could find on this. Oh, it feels like we almost have something here. I just don't know where to take it from here. Eventually, we have a GI. Wait, what if we use a cardinality argument? I'm thinking. So we're gonna take this and we're gonna once more hilariously compress it. This means that G is equal to Langle G1 cup Langle G2 cup on and on cup Langle Gi. I'm going to scroll down. You guys will see my workspace, which means that the order of G is equal to the order of G1. I didn't expect to be making a set theoretic argument today, but you know what? If this works, unit of Gi. Which is equal to G1, the order of G1, plus the order of G2, plus Okay, this is gonna be good. 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 This is gonna be very good. Plus the order of G1 cap G2. On and on, right? Now, the only things we have to care about since the GI was chosen to be disjoint, yes, or G1, G2. Now since each of these were assumed to not divide P, because these are subgroups, they need to divide N. So we need to have it, we can have it be wait, no, N will, the order of the subgroup will divide the order of the group. So we have this set of things which all divide, because the intersections are subgroups too. So they'll all divide it minus the GI. Okay, let me quick think of it, like actually work out the mathematical expression. So the A union B equals A plus B minus A cap B. The cardinality of A union B union C is equal to the cardinality of A union B union C, which is the cardinal. Actually, wait, yeah. A union B cardinality of A union B plus the cardinality of B minus the cardinality of A union B intersected with C. So using this knowledge, this wonderful set theoretic knowledge, we have that G is equal to the cardinality of G1 union G2 union on and on to GI minus 1 plus the intersection of GI plus this whole thing, which we'll just call A, and this whole thing, which we'll just call, yeah, plus A intersection with B. Now what we notice is that these two terms, because of construction, are both do not divide P. P does not divide these terms. Right? So if P also doesn't divide this, Alright, so we know that P will not divide this right here. Or if it did during any process of that, then we would automatically have a subgroup with a element P such, or an element G such that G to the P is equal to 1. So we also have gosh. Wait a minute, let me go back in the reading. I feel like there's some merit to my idea, but I'm just like too scatterbrained in order to like properly execute out on it. Control X. Alright, so I'm just going to be quickly scrolling back to see what they said about this, because they said something about this at the end of the chapter. Alright. Chapter 13. Okay, so finite abelian groups are isomorphic to direct products of the form that so like am I supposed to just assume this result, or are we going to prove it? I'm confused. Let's prove it. Yeah, okay. I think we're just, because they put it at the end of this and they put it in exercises, we are supposed to assume this. So we say that G would be broken down into a factorization. Well, factorization literally as like multiplication of groups, external products. And then because one of those must be some multiple of P, or Pn, then, excuse me. Then Pn, oh god, I can't think right now. Then by some abelianist stuff. Yeah, because one of the integers is z mod p to the n, or p times n. In z mod p times n, we're gonna have always an element with which has order p. So yeah, and since it's isomorphic to that, we just find the element such that that's the case under the isomorphism, and it works. Although I do wish I might be working, just like looking on my own time at marching band today, if we get break, for what actual like constructivist proof, like what combinatorial-esque proof you have, because there's something combinatorial in there, like most definitely. All right. So every non-abelian group of order divisible by 6 contains a subgroup order 6. This is specifically the case of, I think it's a sub 6 or a sub 4. Yeah, a sub 4 is a specific disproof of this. So a GP group of order 20, if G has subgroups H and K order 4 and 5 respectively, such that HK equals KH for all for the G is the internal direct product of K, H and K. This is because if it's not the case that G is the internal direct product, then there's another element. But if that's the case, then the group has order greater than or equal to 20. Prove or disprove the following assertion. Let G, H, K be true. If G times K is isomorphic to H times K, then G is isomorphic to H. So let's think. It seems right, but because it's an external group. But I'm wary to think of it. So, okay. Let phi be an isomorphism of G times H to, or G times K in this case. G times K to H times K. Now, we have an inclusion from g to k, or g into g times k, given by g is sent to g0. And we also have the restriction from h to k, h times k to k to h, defined by h k is mapped to h. Now the question is R v I an isomorphism? Why do I feel like this is something that can fail in the case of infinite products? Yes, actually this is. So like, oh, this is actually this is a very sneaky example. So we're gonna have z is isomorphic to, it's going to also be by its times z. Actually, it's going to be I'm thinking it's going to be something like this. Oh yeah. I'm feeling like there is something that fails at infinity. I'm just trying to phrase it in like how you would phrase it. So z times z is isomorphic to q times z. So we send p and q to p over q. No, that can't be right. Okay. Because the main thing I'm thinking is like, if g times h is isomorphic to h times k, or g times k is isomorphic to h times k. I want a quick, okay, this is the one time, I hate doing this, but just to, so that I don't, oh dang. Dang, I just got hit by another bot. Impressive, okay. Oh gosh. Time out. So if G, yeah, let me just Google this. If G times H is isomorphic to H times K, is G isomorphic to H? Why does my mic randomly mute me? Oh my gosh, okay. I guess that one viewer was just really, well, the one viewer as in Bob was just really mad that I banned them. And so they decided to turn my mic off. But this means you didn't hear me go absolutely crazy about this thing, because this is related to category theory. So, suppose phi from G1 to 2 is an isomorphism, and psi from G2 to G3 is an isomorphism. Should that phi of negative 1? Yeah. Alright, so first, phi to the negative, yeah. Phi to the negative 1 of phi of A, phi of B equals phi to the negative 1 phi of AB equals phi to the negative 1, or no, it just equals AB equals phi to the negative 1 phi of A phi to the negative 1 phi of B. And the one-to-one and onto condition should be obvious from inverses of functions in set. So we have that phi negative, we have that the group operation is preserved. Now, from here, as well, it should be obvious the compositions of two bijective functions are is bijective, and C of phi of AB equals C of phi of A phi of B equals C of phi of A C of phi of B. So the operation is maintained. Later on, you'll learn that this composition property of, more generally rather than isomorphisms, and more generally from isomorphisms, homomorphisms, shows that we can form a category group where we have objects, which are groups, and we have arrows, which are homomorphisms, such that we have a nice composition that allows us to create very pretty constructions. Anyways, I will stop ranting for a second. Alright, so and also, yeah, because these, like, the equivalence relation, if two groups there's an isomorphism between them, first of all, reflexivity ID is one, a isomorphism. Phi of G1 implies phi in negative 1 is an isomorphism. Shows symmetry, and then phi composed of C of isomorphisms with an isomorphism shows transitivity, which shows that we have an equivalence class. Show that U of 5 is isomorphic to C sub 4. Actually, I'm pretty sure this is true. So U of P is isomorphic to Z of P minus 1. So let's think about how we actually prove this. So we want to prove is that the order of G in U of P is equal to P minus 1. So it should be obvious that G to the P minus 1 is equal to G to the phi of P is equal to G to the order of U of P is equal to 0. Wait a minute, let me think. I guess, yeah, one way you can show this is that how do I best say this? Oh god, the thing is, this is like a preview of field theory, because Z of sub P is a field with group ZP. Actually, okay. Because I said that field theory thing, I want to leave that on a cliffhanger, and we'll do that later when we get to fields. Because there's actually a very important result there about the fact that the multiplication group on Z sub P is a group, and discussing some stuff on that. Rather permutation associated with no. Okay, an automorphism of a group G is as an isomorphism with self itself. For that complex conjugation to automorphism. Ah man. This should be an obvious thing, that phi of a plus bi equals a minus bi is an isomorphism, but what is important is that the isomorphism is a certain conjugation, or no, oh god. The automorphism is an automorphism over a field, which defines certain very nice algebraic properties when we study Galois theory eventually. So I'm going to just like leave that there. There's a lot of cool stuff, and a lot of this is like fairly trivial to prove, but like there's so much of it that's going to come up in Galois theory that I feel kind of like a disservice proving this, or disservice leaving this as it is without having the Galois theory behind it. Yeah, okay. All intermorphism. The quaternion group is in G for odd G. G be a group and G divided. Yeah, this is the same thing as was being done previously. Yeah, and this will be the inner automorphism is the fact that it's a composition of isomorphisms. Okay. Let G be the internal direct product of subposition K. Show the map phi from G into H times K defined by G. Which K is 1 to 1 and onto. Show the map phi. So, okay, yeah, I'll do this. G is inner product of HK. And we define phi from G to H times K by G equals HK implies that phi of G equals HK. So if it's not 1-to-1, there's some element phi such that phi of G, so basically let's examine all phi of G that is equal to 0, 0. Well, this is equal to just simply, by how we're defining it, this is implying that G is equal to 0. So 1-to-1 is good. And on to is we just take the element G such that G equals HK. To get HK, we kind of already given ourselves like the tools for talking about that. G has isomorphic groups. If G has a subgroup of order n, prove that H also must have a subgroup of order n. This is kind of just under the relabeling aspect. And it's mainly taking that group, and we have the image of, oh god, this is like, this is something about the book that I particularly don't know how I feel about, because it's trying to go over isomorphisms without talking about homomorphisms. And homomorphisms are just very nice things, and ultimately what this is going to say is that the image of a homomorphism is itself a subgroup. So the image of a subgroup is a subgroup, and the image of a subgroup is has the same order of has order n. Okay, if G is isomorphic to G bar and H is isomorphic to H bar, show that G times H is isomorphic to G bar times H bar. This is applying the isomorphisms component-wise. This is actually more than just the case for G and G bar. It's for any G and K. It's for any G and K, or K, G, and H isomorphic to H, KH. Prove that G times H is isomorphic to H times C. We just take the isomorphism that reverses the elements. Let n1 and k be positive integers. Show that if and only if the greatest common divisor. Prove that A times B is abelian if and only if A times no, I can't think. Okay. Prove that A times B is abelian if and only if A and B are abelian. We would do that by counterexample. If G is the internal direct product of blah blah blah, prove that G is isomorphic to the product of that. Okay. Yeah, this is just, it's kind of interesting, but like not really. Shh. A lot of these are like, there's a reason there are so many exercises, because a lot of these are very computation based and getting used to the flavor of it. So I'm not going to belabor them here. Groups of order 2p. Alright, so groups of order 2p. In this series of exercises, we will classify all groups of order 2p, where p is an odd prime. A. Assume that G is a group of order 2p, where p is an odd prime. If A is in G, show that A must have order 1, 2, p, or 2p. This is just an application of Lagrange's theorem, because these are the only ways that the subgroup can divide the order. And the order of the subgroup in this case would be the order of A. Suppose that G has an element of order 2p, prove that G is isomorphic to Z, 2p, hence G is cyclic. It's because the cyclic group generates the whole group, just by the fact that the cyclic group is a subgroup. C. Suppose that G does not contain an element of order 2p. Show that G must contain an element of order p. Hint, assume that G does not contain an element of order p. So if G doesn't contain an element of order 2p, then G must contain an element of either order p or order 2. If G does not contain an element of order p, it contains an element of order 2. It contains an element of order 2. Now, okay, let me think. So, like, let's actually write this out. G is equal to 2p. Prove that G is isomorphic to C 2p. Suppose that G does not contain an element of order 2p. Show that G must contain an element of order p. So, for all G and G, or actually no, a better way of just saying it is that G is not cyclic. G is not cyclic. Show that G must contain an element of order p. So if G doesn't contain an element of order p, so if G does not contain an element of order p, if G does not contain an element of order p, it contains 2p elements of order 2. Elements of order less than or equal to 2. Oh, that's clever. That is very clever. I like this. So, if contains 2p elements of order less than or equal to 2, right? So, that means that for all 2p minus 1 elements, so for 2p minus 1 elements are of order 2. So let's think. Which means that for any element, wait, give me a second to sneeze. Oh yeah, okay. So then that means for any element G1 and G2, G1, G2 squared is equal to E, right? But this is G1. G1, G2, G1, G2 is equal to, or G1, G2, G2. Wait, no, I was right before. G2, G1, G2 is equal to E, which implies that, first of all, that G2, G1, G2, G1 is equal to G1, G2. So we have an abelian group. I'm thinking, gosh, I'm very glad I'm reviewing group theory because I'm very not fresh off a lot of this. Okay. Assume that G does not contain an element of order P. And assume that G does not contain an element of order P. Let's think. So there are 2p elements of order less than or equal to 2. This means that 2p minus 1 elements are of order 2. I feel like there's something I'm just like centrally not getting here. So if G is equal to, order of G is equal to 2 times the prime. G is not cyclic if G does not contain one element of order P. G is not cyclic. If G does not contain an element of order P, it contains 2p elements of order less than or equal to 2. And we have specifically that 2p minus 1 are of order 2. I think I got it. Okay. So if G1 and G2 are elements, first of all, we already know this group is abelian, right? This comes down to the central squaring fact. So if we have G1 and G2, then we have that G1, G2 is different from G1 and G2. Is different from G1, G2. So for example, we have G1 and then I'm trying to think here. So the groups of abelian we have for any G1 and G2. G1, G2 is both non-zero and different from G1, G2 if G1 is not equal to 2. G1 is not equal to G2. What am I missing? Okay. Oh, this is the process of a math major just like doing the same thing over and over. Shh. Okay, so assume that G does not contain an element of order P. I feel like there should be accountability, counting argument against this, but I can't think of it. I'm gonna grab a drink of water while I'm thinking about this. So. Two P minus 1 elements are of order 2, right? Gosh, okay. Assume that G does not contain an element of order P. Okay. G's not cyclic. Every element is of order 2, so every element squared is equal to the identity. Is it? Is it that what I think it would be is that the number of elements in your group. So basically we have a process where first we pick G1, not equal to the identity, then we pick any other G2, and we form the set of, how do I best describe it? So like we pick G1, and then we pick G2, and we form the group G1, G2, G1, G2. And then G3 we get G1, G2, G1, G2, G1, G3, G2, G3, G1, G2, G3. And we'll have the order of the group is actually a power of 2 instead of 2 times a odd prime. Alright, what I'm going to assume is that should be correct, but okay, let's see that this works. So we have also, let's note here that G is abelian. So we form a process, and this process goes as follows. First, we have G0 is equal to the empty set. G1 is equal to some choice of E, G1. G2 is equal to that explains it, actually. If every element is of order less than or equal to 2, then we can find some subgroup of 2 elements E, G1, G2, G1, G2, yes. Because if an element is of order, if there's not an element of order P, we have at least 2 elements of order 2. And at least 2 elements of order 2, 2 different elements of order 2, gives us the ability to form a subgroup of order 4, which contradicts the order of our group G. So interesting, that's actually a very strong restriction, yeah. Because notice, let's say that order of G1 equals order of G2 equals 2. Then G1, G2 squared. Yeah, because then G1, G2 squared is equal to the identity. So G1, G2 equals G2, G1. And we also as well have a full permutation, like a full subgroup here. Well, that is a nice result. Okay. Suppose that G does not contain an element of order 2p. Show that G must contain an element of order 2. Well, it's mainly that if we have an element of order, no element of order 2p, we have an element of order p. Oh, this is actually really interesting. I'll show that G must contain an element of order 2. So we either have an element of order 1, 2, or p. If we have an element of order p, then we need to have another element outside of that, but it can't also itself have order p, because then we have order p squared, so we need to have order 2. Let P be a subgroup of G with order P, and Y and G have order 2. Show that YP is equal to PY. So B be a subgroup of order P, and Y and P have order 2. So let's do this. So we have that. Also, apologies if you hear a little kitty cat running outside. It is feeding time for the cats. Other people in the household are dealing with that, so P be a subgroup of order P. So P, we let P be a subgroup equals P. P divides G, or P is a subgroup of G. and y and g has order 2. Y is an element that has order 2. Order y equals 2. And suppose that we have an element y g1. Importantly, we have that y g1 p. Actually, no, we don't necessarily have that. So we want to show that if y g1, we have y g1, there's some element g2 in p, such that y g1 is equal to g2y. This can be done by showing that g1 is equal to y g2y is equal to y. Yeah, that's fundamentally how it's going to be done. So suppose that y g1 is in p. We need to show that y g1 y is in p. So the order, or no, y g1 y, well, obviously y g1 squared is not equal to 0. So y g1 to the p is going to be y g1y, y g1y, which is going to be simplified down to y g1y, y g1 y, blah blah blah, which is going to be simplifying down to y g1 to the p, y equals y equals e. So yeah, y g1 y to the p is equal to e, so it's in that subgroup. Because we can't have two disjoint subgroups of order p. Suppose that G does not contain over 2 and P is equals Z is a subgroup of order P generated by Z. True that Y Z is equal to C K for some 2 less than equal to K less. It comes down to another like factorization argument. Let's suppose that G does not contain an element of order 2P, so that G does not contain an element of order 2P. Prove that G is not abelian. So suppose that we have an element P and we have an element Y. Is YP equal to PY? Well, if this were the case, then P would be equal to Y PY. Let's think. Which is the same as showing that. If YP is equal to PY, oh yeah, if YP is equal to PY, then YP is an element of order 2P. Okay, that was actually surprisingly simple. Suppose that G does not contain an element of order 2P and P equals Z is a subgroup of G of order P generated by Z and Y is an element of order 2. Show that we can list the elements of G as Zi, Y to the J. For 0 is less than or equal to I is less than P, and 0 is less than or equal to J is less than 2. Just kind of basic listing things. And suppose that G does not contain an element of order 2P equals Z is a subgroup of order P generated by Z and Y is an element of order 2. Prove that the product Zi, Yj, Zr, Ys can be expressed as a uniquely as Zm, Yn for non-languages Mn. Thus conclude there is only one possibility for a non-abelian group of order 2P, and it must therefore be the one we have already seen, the dihedral group. So prove that the product can be expressed uniquely as ZMYN. Oh, that's actually that's a really nice proof of like the importance of the dihedral group. I like that. Okay. Give me a second. Prove that the product ZIYJ ZRYS. So we have ZIYJ ZI YJ Z R Y S. Suppose that's equal to, let's start by assuming it's true and see what we can derive. So ZM YN, we multiply by YN on the right. Actually wait, uniquely for some non-negative integers M and N. Z to the P minus I. So Y to the J. ZR. Y to the S equals Z to the M minus I mod P YN. Which shows us that then we multiply by YJ ZR is equal to Z M I mod P. Y yeah. M plus P minus I Z to the N plus 2 minus S. The absolute value of this. Yeah, okay. So it's just a simple solution of equations. So it's like a fairly simple solution to some equations. Oh gosh, okay. Yeah, this is a fairly satisfying result. It's a lot, but it's fairly satisfying. Let's conclude there's only one possibility for non-abelian group order to be, that there must be the one that we've seen already, the dihedral group. God, yeah, that is actually very satisfying to see that the dihedral group gives a proper, like, a complete derivation of the dihedral group. Why is important? Anyways, that should have been most of the exercises I wanted to do. A lot of this is, if you're watching this, I would definitely recommend you do some of these exercises on your own. These are very valuable, but for me, a lot of this is review, except when I struggle on things and I learned that I didn't learn it well enough the first time. Don't worry about that. And for review, it doesn't help me much do a lot of pure computations. But especially if this is your first time seeing this, do the computations. We're going to develop more powerful tools later on that help us with a lot of this. But that doesn't mean that what we're looking at now isn't exactly powerful. Yeah, anyways, I guess with that, I was going to say this is extremely exciting, this next chapter. This sets up a ton. But until then, for the sake of time, I'll end stream here. So, thanks for tuning in. Have a nice